about several properties of logarithms. We had like 6 of them that the whole purpose of learning them is because they can help us solve equations. Okay, so the first thing we need to do is discuss this change of base formula. So we discovered that our calculator has a log button and an ln button. The common logarithm, which is base 10, and the natural log, which is base e. So the change, but that's all your calculator can do. It can't, unless you have, I think it's a silver edition, you can put in different bases in that one, but otherwise your calculator can only do those 2 bases. So if you want your calculator to figure out a logarithm for you, you use this thing called the change of base formula. So let's say I have log base b of x, right? And I want to know what that is. I want the calculator to figure it out for me. Well, it's got to be something, right? Some unknown quantity. So let's call it y. All right, so if log base b of x equals y, what exponential equation means the same thing as that equation? B to the y equals x. Okay, so now let's say I want to solve this equation. Because for y, I want to know what y is. That's the whole thing. I don't know what this is, trying to figure it out. So to solve this thing for y, I could take the log of both sides. That's like one of the most fundamental things you learn in an algebra class. Do the same thing to both sides, right? So I can take the log of both sides, and I can actually use any base I want, as long as I do the same thing to both sides. So I'm going to take log base a, some new random base of both sides. Yeah. The whole idea being I could change it to a base that my calculator can do. So now that I've taken the log of both sides, I can use one of my properties of exponents. I'm sorry, my properties of logs that says I can take that exponent. It is, yes. That is supposed to be a y. So I can use one of my properties of logs that we learned last class. When you have the log of something to a power, you can take that exponent and bring it down in front of the logarithm. So this ends up being y times log base a of b equals log base a of x. And then if I want to know what y is, what should I do next? Divide, yeah. Log base a of b is just a number, right? It's just a number. So I can divide both sides by it. So I end up with y equals log base a of x over log base a of b. Right? And y was representing log base b of x. So you can change it to any base you want. Log base b of x would be log x over log b, any base. So the great thing about that is that my calculator can do 2 bases. So I could do ln x over ln b, or log base 10 of x over log base 10 of b. So this is called the change of base formula. So for example, if I want log base 2 of 12, pick a base that your calculator can do, like maybe ln, and you can do ln 12 divided by ln 2. If log base 2 of 12 is 3.585, what exponential equation does this thing correspond to? Equals 12, right? This is how we check our work. Check that 2 to the 3.585 is 12. So I do 2 And instead of writing this rounded number, I'm just going to do previous answer so that I won't have any rounding. And I get 12. So that is the correct answer. That is the number that you raise 2 to get a 12. All right, you guys do log base 6 of 9. So you can do any base you want here. I could do ln or log, right? Whichever one I like. So I'll do log this time since I did ln last time, so you can see that you can do either. Log 9 over log 6. Log 9 divided by log 6. And we get 1.226. Okay, and then to check, what should I do? Yeah, raise 6 to this power, and then what am I expecting to get? If I do to the previous answer, I should come right out to 9. Yeah. You don't round. Good. All right, so now we have this really nifty tool. This is really helpful. We can find any log we want without having to solve graphically all the time, which is what we were doing before, right? If I had asked you to find log base 6 of 9 2 classes ago, you would have said, well, that means, well, it's got to equal x. I would have said 6 to the x equals 9, solve graphically, right? Now I can do it without solving graphically. Yeah. So learning how to solve exponential equations allows us to solve those how long problems or how old problems that we've been looking at and only had the opportunity to solve graphically. So things like, how long will it take for college tuitions to double? How long will it take for your BAC to drop below 0.1% if your body processes a third of the alcohol in your system each hour? The question about the Egyptian burial cloth, right? We could figure that was a how long ago or how old is it? We can answer those questions now. So we're going to start with some simple ones, and they're going to get progressively more and more complicated. So I want to solve 2 to the x equals 72. I'm going to do 2 different methods. You can pick the one you like. Okay. So if 2 to the x equals 72, I can take the log of both sides. Any base I want, as long as I do the same thing to both sides. So I'm going to use the ln because it saves me from writing a letter. Just have to write 2 letters instead of 3. But it does not matter. You can pick whichever base you want. But the whole purpose of taking the log of both sides is that it's going to let me use that awesome property of logs that will take exponents down from the exponent. I can get the variable now down out of that exponent. Just apply that property of logs, and now I have x times the ln of 2 equals the ln of 72. And then what should I do if I want to know what x is? Divide both sides by the ln of 2. Because the ln of 2 is just a number. Cancels out there, and I get x is ln 72 over ln 2. And that comes out to ln 72 over the ln of 2 is 6.17. With the ln 72 over ln 2, why isn't that just 72 over 2? Because when you cancel things, it's a good question. ln 72 over the ln of 2 is not 72 over 2 because ln is a function. That would be like, it would be like writing f of 72 over f of 2, right? And canceling the f's because they're not variables, it's just the name of a function. Okay, so my second method here, I have 2 to the x equals 72. Because 2 to the x has a base of 2, I'm going to do the same thing I did before where I can take the log of both sides, but I'm going to take log base 2 because the base in my 2 to the x is a 2. And you'll see why as soon as I write it down. If I have log base 2 of 2 to the x equals log base 2, 72. Now I can use the definition of log as the liftoff function, right? My bases match. I have log base 2 of 2 to the x. What is that? X. You just lift off the exponent. And it equals log base 2 of 72. So now I know what x is, but if I want to get a decimal, I have to put that in my calculator. And what tool do I now have to do that? Change of base. So this is ln 72 over ln 2, which is exactly what I got using the other method, which is approximately 6.17. So the two methods are actually very, very similar. We just take the log we take of both sides, the base differs, but then you end up changing the base at the end anyway. Okay, you try the next one. So I saw a couple of different things that were really the same thing. Okay. So most people took the ln of both sides. Okay. Because whether you decide to take the ln of both sides because you like taking the ln of both sides in all scenarios, or you took the ln of both sides because ln is log base e and this is base e, either one, most people took the ln of both sides. So we have the ln of e to the x equals the ln of 25. Now, I saw several people apply the property of logarithms that brings the exponent down in front. So this says x ln e equals ln 25. And then to get x by itself, divide by the ln of e. Cancels, cancels, and we get x is ln 25 divided by ln e, 3.219. Thank you. Okay.
I don't know if I'm looking ahead here, but I just kind of skipped that step and did the liftoff.
Yes, that's another way to go about this. So let's say if I have ln e to the x, so starting from the first step here, equals ln 25. ln is log base e, right? So the ln of e to the x should just be x, just lift off, right? The bases match, so you can just lift off, and you get the ln of 25, which is approximately 3.219. Now, how is it that the ln of 25 is the same number as the ln of 25 over the ln of e? Why are they equal?
Because the ln base e.
Uh-huh. Yes, and then when you lift off, you get 1. The ln of e is 1. That's really a 1. When you lift off the exponent, you just get 1. So the ln of 25 over the ln of e is really the ln of 25 over 1, which is the same thing as the ln of 25, which is what we got here. So we've solved things graphically so much over the past 2 days, we're not going to go through solving this one graphically. Okay, so now we have some slightly more complicated looking equations to solve. 2 to the 1 minus x equals 3. I've got a variable in the exponent. My go-to tool when you have a variable in the exponent is take the log of both sides. Okay. Any log you want. I like the ln. You might like the common log. You might do log base 2 because the base is 2 here in the exponent. Either way, however you do it, we can now apply the property of exponents that lets me take this exponent and put it down in front. So I have 1 minus x times the ln of 2 equals the ln of 3. Now, anyone have any ideas? Divide both sides by ln 2. Yes, I can definitely do that. Any, what else could be a reasonable next step here if you decided not to do that? What if this said 1 minus x times 5? What would come naturally? Distribute. You could distribute here also. ln 2 is just a number. So it doesn't matter which one you do. As long as you're always doing the same thing to both sides, you're fine. So over here, we're going to cancel, and I have 1 minus x equals ln 3 over ln 2. And you just have to keep telling yourself, that's just a number. That's just a number. Because it can look overwhelming. And if it gets overwhelming, change it to a number, right? Write ln 3 over ln 2 as its decimal approximation. ln 3 divided by ln 2, and we get 1.585. And then you can use, in order so that the rounding errors don't compound while you do a problem, you can either use second answer so that you don't round it when you're doing it in your calculator, or you can save this number as the letter A and then use that. So the way you store a number is this STO button, second up from the bottom. So you do store, and it's going to take my previous answer and store it as whatever I tell it to. I'm going to tell it to store as the letter A. So I hit alpha A, enter. Now, anytime I want to do something to this number, I can just call up A. And then there is no way to clear it. You just overwrite it. If you want to store something else as A, just hit store alpha A, and it'll just overwrite this one. And you can store it as any letter you want. Get the whole alphabet there. So now that I have 1 minus x equals 1.585, what should I do? Subtract 1 from both sides. Okay, so I get negative x is 0.585. Divide by negative 1. So I get x is negative 0.585. And if I want to be super accurate, just to demonstrate how you do this thing with the A now, I would say, okay, I'm going to take A and I want it to subtract 1, minus 1, and then divide by negative 1, and I get my answer, negative 0.585. All right, so any questions? All right, so let's take a little look at the next one. Does anybody remember my really terrible joke about the mathematician, the physicist, and the engineer?
Yes.
Okay, so the whole, can you remind us what the moral of the story was? Yeah, if you see a problem that you don't know how to solve, try to transform it into a problem you do know how to solve. Okay? So I now know how to solve things that look like a number to an exponent equals another number, right? I know how to solve something that looks like, say, 2 to the x equals 72, or e to the x equals 25, or even something like this, 2 to the 1 minus x equals 3, right? I know how to solve a number to an exponent equals another number. So I want to make this look like that. So subtract 100 from both sides. So I'm trying to isolate the exponential piece. So I get negative 100 e to the 0.03 t equals negative 90. Then what? Get rid of the minus 100 by dividing it out. So I get e to the 0.03 t equals 0.9. Now this we know how to solve, right? This looks just like, or very similar to part A, when we solved in part A. So what should I do to go from here?
What I would do is I would take ln of 9.
Yes, so we're taking the ln of both sides. Yeah. Yeah, this is exactly what you're doing. I'm just writing it out. Yeah. So what is the ln of e to the 0.03 t? 0.03 t, because ln is log base e, bases match, just lift off the exponent. So I get 0.03 t equals the ln of 0.9, and now just divide by the 0.03. So we get t is approximately ln 0.9 divided by 0.03, negative 3.5. Okay? All right. So here's what I want you to work on in your groups. We've set this problem up before, and we have solved it graphically. Now I want you to set it up again, and this time solve it using logs. So I will remind you, this is the formula for interest compounded n times per year. Let's go through it together. So I'm going to start plugging the things I know in here. My principal is $5,000. R is my interest rate as a decimal, which is 0.024. And n is the number of times I compound per year. And if I'm compounding quarterly, that would be 4 times. To the nt, so it would be 4 t, leaving t as the variable because I'm solving for how long, until I get $15,000 in the account. So here's the equation I want to solve. We've done it graphically before. To solve it algebraically, I'm going to simplify it as much as I can before I start using my new tool of logarithms. So the thing in parentheses simplifies to 1.006. Do 0.024 divided by 4, and then add the 1. And now, what should I do? Divide by 5,000. That's the only thing I can do, because I can't multiply 5,000 times 1.006 because of the order of operations. It says that I would have to do 1.006 to the 4t first before I multiply. So the only thing I can do is divide by 5,000. And I get 3 equals 1.006 to the 4t. Now I have a number to a power with a variable equals another number. My go-to tool here should be ln. And the reason that's my go-to tool is because it can get variables out of exponents. It can allow me to take the 4t that's in my exponent, bring it down in front of the ln. It's one of the properties that we learned last class. So I have the ln of 3 equals 4t times the ln of 1.006. And this is all multiplication. This is 4 times t times the ln of 1.006. So how do I get t by itself? Yep, I'm going to divide by 4. That will get rid of the 4. And I'm going to divide by the ln of 1.006. So you can do it all in one step like this, or you can do one at a time, whatever. Should, and then by 4. Yes. Yep. If you divide, you can do the division one at a time, or you can do it all at once. You just have to be careful when you're putting this in your calculator to put parentheses around the denominator. 4's will cancel, ln's cancel. So I get t is approximately so I got to do ln of 3, oops, divided by putting parentheses around my whole denominator, 4 times the ln of 1.006. 45.9 years.
Maybe we have a clock that has 3.9 years have passed on it on each day.
So moving on to a mixed kind of equation. So this is called a mixed type because in all the equations that we've solved so far this class, the variable has appeared only in the exponent. Now I have variables in exponents as quadratic terms and as linear terms. I have variables all over the place. Okay, so in every other equation, the variable has been only in the exponent. But what do you notice about, if you just look at the left side of the equation, both terms have an e to the x in them, right? So it could factor out an e to the x. So this would say e to the x times x squared minus 5 equals 0. Factor out the e to the x. Now I have two things multiplied together. I'm doing a multiplication problem. Yes, it is minus 5x. Thank you. So I have a multiplication problem. The answer is 0, which means one of my factors has to be 0. So either e to the x is 0, or x squared minus 5x equals 0. At least one of them has to be 0. Yes, Dylan. It cannot, correct. How do you know that? Yes, 0 is the asymptote for e to the x. If I draw a graph of e to the x, it looks like this, right? And my graph never gets down to the x-axis, which is y equals 0, right? So this has no solutions. E to the x equals 0, never.
Well, like even if you put x is 0, it would be 1.
Right, because even if you plugged in 0 for x, you'd have e to the 0, which is 1 and not 0. And if you start plugging in fractions, you're going to be taking square roots or cube roots, which will never give you 0. And if we plug in negative numbers, you're going to get 1 over e to the something, which are going to give you really, really small numbers, but never 0. So that never happens. Somebody have their hand up over? Do you have your hand up? Okay. So that means that this is the only thing that can be 0. So I solve this one by factoring, and I get x equals 0 or x equals 5 as my two solutions. Let's do a quick check of this. We should be in the habit of checking our answers. I I like to, especially when the equation's a little bit complicated looking, like this. I mean, it's not too bad, but it would be easy to make like an order of operations mistake or a typo or something like that. So what I like to do when I have something like that is use y equals. Put that function into y equals x squared times e to the x minus 5x times e to the x. And then I can have my calculator plug in a 0 and a 5 for x. And if I get 0, I'll know that I did it right. I'll know those solutions are correct. So I can use my table. I plug in x is 0 and x is 5. I get y is 0 in both cases. So I know that my solutions are correct. I think I just said I can use my table. Press second graph.
That's a different way
of checking? Yes. The other way to check is to just type it in. I would do 0 squared times e to the 0 minus 5 times 0 times e to the 0. Type that all in and I get 0. But it's just a lot of typing, especially if I have to check another one. Right, so I like to use the y equals. It avoids making silly calculator entry mistakes. All right, so here's another one, very similar. You try. Okay, I'm seeing sort of two approaches here. One is following the same outline I gave you in the last problem, with a slight twist, right? There's a 10 to the x in every term here. So if I move the 2 times 10 to the x over, I can factor out 10 to the x. Okay, so now there's a 10 to the x in every term. I can factor it out. It's like a reverse distribute. And I just get x squared minus x minus 2. And now I have a product. Multiplying two things together, the answer is 0. So either 10 to the x is 0, or x squared minus x minus 2 is 0. 10 to the x equals 0. Never, right? It's got the same shaped graph as e to the x. It will never be 0. And this one you can solve by factoring or the quadratic formula. This factors to x minus 2, x plus 1. So we get x equals 2 or negative 1. Yeah, Lisa? No. No, you were not. So the question was she cheating if she just divided out the 10 to the x? So if I have 10 to the x times x squared minus x minus 2 equals 0, is this the point where you divided? Okay, so she thought to herself, I'd love it if that 10 to the x just wasn't there, right? I will divide both sides by it. In this case, it's okay, right? It's okay because the reason that we're often hesitant to divide by an expression that has a variable in it is that that expression might be 0. And if it is 0, we've broken, like, you know, the one law of math that you should never break, divide by 0. But we know that 10 to the x can never be 0. So it's okay to divide by it. I have not ruined the universe. And 0 divided by anything is 0. So, and then we end up with x equals 2 or negative 1. So 2 approaches. Do whichever one you like. Okay, so moving on to solving equations that have logs in them. So solving equations that have a variable in the exponent, you use logs. To solve a log equation, change it to an exponential equation. Okay. So first we want to isolate the log, so I think I'll divide by 2. Get the log by itself, so I get the log of 5x equals 2. Now there's no base written there, so what base is it? 10. Okay. And then what exponential equation corresponds to this log equation? 10 squared equals 5x. 100 equals 5x is an easy equation to solve. Divide both sides by 5, and we get x is 20. What's the matter, Garrett? Where? This step right here? This is the definition of a logarithm. This is 10 is the base in both equations. 10 is the base. A log is an exponent. So my exponent is the 2, and it equals 5x. So this was the definition of a log. It said if I have log base b of x equals y, that means the exact same thing as b to the y equals x.
So it's really different numbers.
Yeah. Okay, so now I've got 2 logarithms in the same equation. Yeah, so the only thing I know how to solve, the only technique I have is to change a log equation to an exponential equation. So I have to have log of something equals something. That's the only thing I know how to do. So, I mean, a good first step would be like, okay, I'll put all the logs on one side. Yeah. Pour the water on the floor. 2 minus, oops, what am I doing? Plus log base 2 of x equals 2. Oh. Okay, so now I have 2 logarithms added together. They're the same base. Can I combine them into a single logarithm? It's not log base 2 of 5x. It's not, you can't add the 4x and the x, but log base 2 of 4x squared. This is one of the properties we learned last class. To combine these into a single logarithm, I combine them using multiplication. Multiply the 2 inputs, 4x and x, and that will combine them into a single logarithm. I'm going to write down the rule for you to remember. The log of a times b is log a plus log b. So I was given a log a plus a log b, and I wrote it as the log of a times b.
It's just like combining like two.
Kind of, yeah.
I was thinking of it in terms of the plus and the minus that you can't see.
Right. So now I can write this as an exponential equation. 2 is my base. This 2 is my base, so I have 2. This 2 is my exponent, and it equals 4x squared.
So is this is it factoring out?
No. This is different than factoring out. This is switching a log equation to an exponential equation using the definition. So the log goes away. Nope. I'm using the definition of a log that says log base b of x equals y is the same thing as b to the y equals x. So I'm writing a sentence. It's like writing a sentence using synonyms, right? It's the same meaning, different symbols. So now I'm going to divide both sides by 4. And I get x squared equals 1, which means x is what? Plus or minus 1. We were right here. All I did was divide both sides by 4.
How did you get there?
I was changing this log equation to an exponential equation. Okay, so my base is 2. Base is always 2. Bases are the same. Yep. And then the exponent is also 2. That's this guy. 2, 2. And then it equals the input of the log. So the input of a log is the output of an exponential. Because logs and exponentials are inverses. Yeah, well, when I solve this equation, I get plus or minus 1. Let's check our answers, though. Go back to the original equation. Log base 2 of negative 4, what is that? Log base 2 of negative 4 plus log base 2 of negative 1 equals 2. Yeah, log base 2, you can't take the log of a negative number because it's you're asking yourself, what power should I raise 2 to get a negative 4? This, trying to evaluate this, stop, Audrey, come on. When I write log base 2 of negative 4, if I ask you to come up with a number, what does that equal? An alternate question, I could ask it, rephrase the question as 2 to what power would give you negative 4? But there is no such power. There's nothing you can raise 2 to get a negative number. So negative 1 is not one of my solutions. It's just x equals 1. Right, it's a non-real answer. Okay, this one is similar to the last one. You try it.